Today we want to talk about the gradient. It's going to be us combining partial derivatives and vectors. We're going to combine partial derivatives and vectors, two great tastes that taste great together. All right. Does anybody even know what that refers to? I got to update my references. I'm like talking about The Matrix. That's an old movie. And I'm talking about two great tastes that taste great together. That's an even older reference than the Matrix. It's Reese's peanut butter cups.
That.
Is everybody familiar with the Reese's peanut butter cup? There used to be a commercial for Reese's peanut butter cups.
Okay.
And it was like two people walking along the street headed towards a corner.
Right,
One of them had a chocolate bar and they were munching on the chocolate bar.
You put stuff in.
Right. And then the other person was walking along the street with a jar of peanut butter and a spoon. And then they bump into each other and then the chocolate bar gets dumped into the peanut butter. And like, oh, you got your chocolate in my peanut butter. You got peanut butter on my chocolate. They're both eating it. This dude had a chocolate bar, was in his mouth, is now in the peanut butter.
Yeah.
And he's like, oh, well, I'm gonna eat it anyway. And they both agree. So it's like, oh, well, do you want to split this with me? Second of all, this dude is walking down the street with a jar of peanut butter and spoon. I'm not saying that I haven't had like a spoon and like got the peanut butter and like was walking around the house, but I filled up the spoon and I was walking around the house. I wasn't carrying the jar with me and I wasn't walking down the street. I was like, oh, I'm going to take a walk with my peanut butter. That's truly living. I think I need to try that. I'm glad I recorded that. Anyway, partial derivatives and vectors. That's right. Two great tastes that taste great together. You got your vectors in my partial derivatives. You got your partial derivatives all over my vectors. We're going to start with the gradient in the plane. Gradient is in the plane. This is a gradient is a thing that we're going to apply to a function of two variables. It's a thing that we're going to apply to a function of two variables. It's going to involve the two partial derivatives, fx and fy. The gradient of f is given by our abbreviation for the gradient, our notation for the gradient is just to say gradient of f. Since it's the first time, I'm just going to write gradient of f of xy. It's something that we're applying to a function of two variables. Is fx at xy I plus fy at xy j. The I component of the gradient is the partial derivative with respect to x. The j component of the gradient is the partial derivative with respect to y. A lot of times we'll just leave off the of xy part to save on some writing. So we might just write grad f is fxi plus fyj. Relying on our ability to remember that fx is a function of x and y. It's a function of two variables. But we also want to remember that this is a thing that we can evaluate at a point. This makes sense. The derivative is a thing that happens at a point. The derivative is a local calculation. What's going on at this point? Another abbreviation for the gradient of f is to write an upside down capital delta. And we pronounce that as del. So we'll say del f.
So reverse it. Take it straight.
Yeah. It's just an upside down triangle. It's an upside down delta. So that is del. It's just an upside down triangle. That doesn't make any sense. Triangles don't have a default orientation. It's an upside down delta. Now we're being specific. The triangle with the flat part on top. That's called the del operator. So you might hear the gradient of f or just del f. Just looking ahead, this is going to be, we're going to edit this part out, but this is in the director's cut. The del operator is where we get turn our function and the partial derivatives into a vector. The del operator itself is a vector, but not like just a constant vector or a variable vector. It's an operator vector. It's the partial with respect to x I plus the partial with respect to y j. When we apply the del operator to things in R3, there'll be a partial with respect to z k. It's not a vector that we could just draw. It's a vector operator. So when I apply this vector operator to a function, it says take the partial with respect to x and make that the I component, and the partial with respect to y, make that the j component. And if I have a function of 3 variables, take the partial with respect to z and make that the k component. So the del operator is a vector and also an operation operator. Question? Yeah, we could rewrite it into a function of 3 variables. We need a function of 3 variables. We could rewrite a function, an equation of 3 variables, and then take partial all the way through. Right now, we just want to consider a function of 2 variables. Now, remember when we picture a function of 2 variables, we're picturing a surface, a 2-dimensional surface in 3-dimensional space. So recall. A function of 2 variables is a 2-dimensional surface in R3. We want to imagine a 2-dimensional surface in R3. Now we want to think about what the gradient is going to be telling us. I was trying to make some numbers work in my head and they're not going to work, so I'm just going to deal with it. I have to learn to cope. Let's grab something where we already know what it looks like. Let's grab a surface where we already know what it looks like. Oh, this is gonna be our function. I'm still thinking about trying to make the numbers work. And I already picked my function, so get over it. That was me telling me to get over it, not me telling you to get over it. So I want to find the gradient of f at this point. 1/2 and then √3/2. We're going to be looking at this from the top. I don't know why I was so worried. I'm going to multiply by 2. I can't get over it. I want to drop us down to the XY plane. So I want to find the gradient of this function at this point. This is a derivative. It's going to be a vector made up of partial derivatives. That's just the mechanical bits that go into finding the gradient. I need the partial with respect to x. The derivative of 4 is 0. The derivative of minus x squared is minus 2x. Y squared is a constant term, so the derivative is 0. And I need fy at xy. Similarly, we get negative 2y. So the gradient will be negative 2xi minus 2yj. We get that vector. I did pick an easy example. I'm not going to make myself work hard. That's like, if I get to be in charge of that, why would I pick hard work? That's like,
Don't do free work.
why would we ignore like millions of years of evolution that keeps us, that tells us to not work any harder than we need to, and then suddenly decide that we need to work harder than we need to? Does that make sense? When you don't want to do something, that's evolution saying, dude, conserve your energy. You might be chased by a tiger later on. And you're like, oh yeah, 100%. So like when you're like sitting at home, just kind of like playing video games. It's like, oh, what are you doing? You lazy child. You're like, oh, dude, I might be chased by a lion later, and I'm gonna be ready for it. Conserving energy. And then you high five your cat who's sleeping next to you. I mean, that's just smart. That's just good strategy. So we know when we plug in the point 1√3, we're going to get a vector. Let's see what vector we get. So the gradient of f at the point 1 square root of 3 is going to be negative 2 times 1i minus 2 times √3j. No, that's about as nice as it's going to get. Negative 2i minus 2 times the square root of 3j. What we're interested in doing is looking at this from the top down. And then I'm going to give you the interpretation of the gradient. I want to think about where this point is. Well, I did think about it already. This point is sitting on the XY plane. Let's find that out. If I find f of 1, 3, not gradient of f at 1, 3, just the f at 1 root 3, I get 4 minus 1 squared minus the square root of 3 squared. So we're at the point 1 square root of 3, 0. So we're on the XY plane. If we look at this surface from the top, we know the level curves are all going to be circles. So for fixed values of z, we're looking at circles. There's the point 1 square root of 3. What we're interested in is what this gradient vector looks like. So here we're at the point 1 square root 3. So the direction that this gradient vector is going to point is -2 in the x direction. So -2 in the x direction and -2 over root 3 in the y direction. So it's going to point right back towards the center of the circle. The actual length of the vector goes all the way through the circle. I just want to point back towards the circle. Let's find the gradient of f at -2, 0. So the gradient of f at -2, 0 is going to be -2 times -2 I plus, minus 2 times 0 j. So the gradient at -2, 0 also points back through the circle. Now let's think about where we are on this surface. This is just where we're at when we cross the XY plane. Above the XY plane is going to be some circular paraboloid with the highest point at 0, 0, 4. The gradient is pointing in the direction of maximum increase. It's going to be the steepest path up the surface. So the gradient is telling us the direction of maximum increase. That's not us concluding that. That's just me telling you that the gradient is pointing in the direction of maximum increase. So the gradient of f at a point xy is the direction of maximum increase. It tells us which direction to go. It tells us the steepest path along the surface. It's the steepest path along the surface. Or the steepest direction. It's the steepest direction at a given point. One of the things that we want to notice about it is that the gradient is going to be perpendicular to the level curve. So notice that if we're pointed directly back towards the center, that is perpendicular to the tangent. So that's another thing. The gradient is perpendicular to the tangent. The gradient will be perpendicular to the tangent of the level curve. One more thing that we can point out, the magnitude of the gradient at that point will be the maximum amount of increase at that point. Will be the maximum increase at that point. That's just restating the steepest part. It's not all, that's just adding extra to this steepest direction at a given point. It's not only the direction, it's the steepest amount. It's going to be the direction of greatest increase. What we want to think about. We need to think about the gradient being perpendicular to the tangent, why that makes sense based on what we know about vectors, based on what we know the gradient is trying to tell us. So this is going to follow up with a, but why though? And at this point, we have encountered a question that I will not be answering today.
Try to keep the enthusiasm.
I don't know about enthusiasm.
And
I just
Agent?
have to keep you guessing. By the way, guessing is the best thing to do. It's all we have. If we don't know stuff, the best we can do is guess and then improve our guess, right? You know what I mean? Sometimes we get to try to avoid guessing because someone else will say, nah, that's not how, that won't work. This will work though. And we can be like, oh, okay, I've seen you do this and it does work. So yeah, I'll go with that. Or we could be like, oh, nah, I think it's perfectly safe to eat this plant. And then the next person that observes that interaction says, you know what, I'm going to trust that person and not eat that plant. You know what I mean? It's like when a car company is like, oh, we're going to do everything different. And then they quickly start finding out why things are done a certain way. It's like, oh, there was a reason that these things were done that way. Gotcha. And you had figured it out a long time ago.
Are you, yeah, yeah.
No, I'm not picking on any particular manufacturer or any particular vehicle. I don't want to name any names, but their initials are Tesla Cyber.
Not bad, okay, give it a sign.
So. It's like, well, this is the way we've always done things. That's never a good way to start, right? That's never a good way. It's like, well, we do this because this is what we've always done. You can't just say no to that though, right? You have to say, but why have we always done it that way? It's never okay to just say, because I usually say, if we do something the way that we've always done it, that's not a good reason to do something. But if you follow that up, it's like, well, this is the way you've always done it, but why though? Because stuff doesn't work. You can't put all the electrical systems and give them a single point of failure. It's too susceptible to that one failure. It's like, so this is the way we've always done things, and this is the reason we've done it that way, right? But if it's like, oh, this is the way we've always done it, and then it's like, oh, but why though? And it's like, oh, so we can discriminate. Oh, wait, maybe we shouldn't do it that way anymore. You see what I mean? My overall point is that Elon Musk is dumb, and he proved that he's dumb every time he speaks or tweets, whatever. What are we talking about? Oh, yes, gradients. So the gradient tells us the direction of maximum increase. And the gradient is going to be perpendicular to the level curves. The gradient is going to be perpendicular to the level curves. The magnitude of the gradient will be the magnitude, the maximum amount of increase that we can see. We go in that direction with this maximum increase, that's going to be the most. We need to think about why that is. We need to think about why that is in terms of vectors. Any questions? Comments? Snob remark? Let's think about some other things that might happen. Let's grab this function completely at random. Function that you're totally unfamiliar with. Let's write down the gradient first. So we need the partial with respect to x. With respect to x, 8y cubed is constant, 12x squared. The derivative is going to be 12x, 24. No, I can't save it. I'm in trouble writing today. So 24x minus 24y in the I direction. And in the j direction, 24y squared minus, that's constant, 24x. Now recall, this function has a local maximum at the point 1, 1. This is a function that we're familiar with. This is a surface we're familiar with. We had a local maximum at 1, 1. This is a function that we dealt with before. We had a local maximum at 1, 1 and a saddle point at 0, 0. If we look at the gradient at 1, 1, what do we get for the gradients at the point 1, 1? 0. We get the 0 vector, not just 0. So if you just want to write 0, this is not enough. That's 0, the scalar. We want to make it the 0 vector. So we can say 0, we put an arrow over it, then it's the 0 vector. You could also just write out 0i plus 0j. 0 on its own, that's a scalar 0. We're looking for a vector here because it's the gradient. So watch your notation. I suppose we could always also pointy brackets. But that always looks like it's watching me, so I don't really like that one. Exactly. It's like that makes it creepy. So the gradient is supposed to be the direction of maximum increase, and we don't really have a direction of maximum increase because we're sitting on top of a hill, right? So it's like there's no difference in which way we go. It's always changing the same. That's kind of how we can interpret it. But what's happening at 0, 0? You had a saddle point. So we end up with the 0 vector again, because we just plug in x and y equals 0, we get 0 vector again. But we can increase from this saddle point. In one direction, it's falling off, but in the other direction, it is increasing. It's just that we can't determine that based on the gradient. Although we do have a way of finding critical points. It's where the gradient is equal to 0. So connecting the gradient to stuff that we've done in the past, setting the gradient equal to 0 is the same as setting the two first partial derivatives equal to 0. So we do have a new way of finding critical points, which is not a new way of finding critical points. It's just a new way to say that we're going to find critical points. So gradient, it's partial derivatives plus vectors. The I component is the X derivative. The J component is the Y derivative. The gradient tells us the direction of maximum increase. The gradient will be perpendicular to the level curve. We're going to say perpendicular to the level curve in the same way we say normal to a surface. We mean normal to a tangent to the surface. So normal or perpendicular to tangent of the level curve. And we'll just say perpendicular to the level curve. And we want to explain why the gradient should be perpendicular to the level curve and indicate the direction of maximum increase. That's what you want to think about. Not actively, because it's lunchtime. So you're going to go eat something, but running in the background, it's like, why is the gradient, the direction of maximum increase, perpendicular to the level curve? And I know you're thinking, there's no way I'm going to be thinking about that. You're not going to be thinking about it actively. It's going to be running in the subconscious because that's how inception works, right? I just put the idea out there. Your brain can't not think about it. No one is that skilled in shutting their mind off. If you're thinking, I'll watch TV, that's just going to give it more room to work with. Because there's like nothing going on in your brain when you're just watching TV. It's like more restful than sleep. During sleep, you don't have an outside stimulus to entertain yourself. You have to make some stuff up. So it's like, well, I'm not watching TV. I'm going to make up a dream. And then all of a sudden, you're like running through the woods being chased by, I don't know, your math teacher from 2nd grade. But they're a vampire werewolf now. And why can't you find a tree to climb, right? And you have to go to the bathroom, which is extra annoying.
Right? Are you speaking from personal experience?
No, not at all. All right, so that's what I want you not thinking about. Why is the direction of maximum increase going to be perpendicular to the level curve? And there's going to be a discussion question for it. So that's it for today. I will see you all on the morrow. Everybody have a good day. And thanks for playing. And watch out for your vampire werewolf 2nd grade math teacher.